Class example 1.44 asks us to determine the equation of a transformed function. This is often rather difficult because it asks us to work with transformations in unconventional orders, which is to say we're transforming an already transformed graph or function that may have been translated and now we're stretching it or reflecting it. But if we take a step-by-step approach and use a graphical confirmation, we should feel quite confident in our answers. Let's start by looking at the function f of x equals 3 times the square root of 6x plus 1 after we transform it with a vertical stretch by a factor of 4 and a vertical translation 6 units up. Writing this in terms of f of x, we see that the vertical stretch by a factor of 4 would give us a coefficient of 4. And a translation 6 units up would give us a constant term of 6. If we now want to determine our equation in terms of x, we simply replace f of x with its corresponding expression of 3 root 6x plus 1. If we multiply this by 4 and add 6, we will get a simplified equation that corresponds to our transformed function g of x. Now, how can we use our graphing calculator to confirm this answer? We'll start by graphing f of x and g of x on the same graph. You'll notice we've adjusted the window settings. You may have to play around with this, but for now, just use the ones we've presented for you. Because both of our transformations were vertical ones, both the stretch and the translation, any two points with the same x-coordinate will be corresponding points. For example, if we determine the value of both of the y-intercepts, we would see that 0 and 1 has mapped to 0 and 10. We can confirm this in our mapping rule, where xy becomes x and 4y plus 6. If we replace x and y with 0 and 1, we see that the point 0, 1 maps to 0 and 10. We don't need to limit ourselves to only the y-intercept in this case. We could also check the point, for example, 6 and 19. Under our mapping rule, we will see that it maps to the point 6 and 82. Confirming that these 2 points appear on our transformed graph is probably reasonable confirmation that we have correctly determined the transformed function. The second part of class example 1.44 becomes a little bit more complicated because now we will work with vertical transformations and horizontal transformations at the same time. Here, we have a reflection in the x-axis. That's a vertical reflection. We have a stretch about the y-axis, which is a horizontal stretch, by a factor of 1/2, and then we translate 3 right. The reflection in the x-axis shows up as a coefficient in front of f of -1. That's the a value. The horizontal stretch by a factor of 1/2 shows up as a b value of 2. And then our translation of 3 units to the right shows up as x minus 3. Because the stretch happened first, the x minus 3 will be bracketed. In order to work on our equation in terms of x, we're going to be a little bit inconsistent here, and I'll address that in a minute. First, I will treat the vertical reflection as we treated our transformations in the previous example. That is to say, I replace f of x with its corresponding expression of 3 root 6x plus 1, and then apply the transformation, which in this case is a negative coefficient. Note that because we've bracketed the expression, that negative sign will multiply to the 3 root 6x, and also to the positive 1. Dealing with horizontal transformations is a bit trickier though. Really the only option is to write them as replacements. So here, because in the expression, that first line, instead of having f of x, we had f of 2 times x minus 3, we will here replace the x with 2 times x minus 3. This might make our equation look a little bit clunky, but I do believe this is the most effective way to determine the equation of transformed functions. We can simplify by multiplying the 6 by 2 to make 12, and then the 12 by both the x and the negative 3 to make negative 36. Notice that that negative coefficient has now multiplied to both the 3 and the positive 1. We can also leave the radicand in a factored form, which is to say 12 times x minus 3, which is somewhat more appropriate if we're wanting to graph it. So let's go ahead and graph f of x against h of x. Here, because we have both horizontal and vertical transformations, we won't just look at points with the same x value, but it might make sense to track the end point. Our mapping rule shows that because we stretched by 1/2 and moved 3 to the right, and because we had a vertical reflection, all points xy become 1/2 x plus 3 and negative y. Transforming the point 0 and 1, we find our new vertex or endpoint of 3 and negative 1. While they may not be as obvious to follow, we can also take another point, such as 6 and 19, and map it to find that it gives us 6 and negative 19, and confirm using a table of values that both of these points lie on our two graphs. Hopefully that helps clear up a little bit about how you can deal with vertical and horizontal transformations on equations.